that working? Is that being shared?
No. Already. Yeah. The red line.
Okay, cool. Awesome. Yeah, I just thought we could go into a bit more about machine learning. It ended up being more about tree-based models today. I wanted to talk about supervised principal component analysis as well, like a high-dimensional data technique. That was actually the thing that made me want to do today, because often we get big data sets with a lot of predictor variables. Maybe think about proteomics, genomics, huge survey data, high-dimensional survey, huge test batteries, and we want to predict some outcome. And so I wanted to talk about methods for that. But I ended up sort of focusing more on trees, and I thought I'll do that today. And next time I'll talk about dimension reduction, factor analysis, principal component analysis, and so on. But yeah, so today we'll be talking more about trees, decision trees, random forests, and XGBoost, and also an ensemble model. Superlearner, there's various ones, but I chose Superlearner. And we're going to talk about some, the purpose of machine learning and as well as statistics. So I guess with machine learning, typically the goal is making predictions. So we use different techniques sometimes to what we do in classical statistics. Having said that, sometimes linear models actually work quite well in prediction. And in particular, generalized linear mixed models are actually quite good in terms of prediction when we've got nested data, repeated measure data, or clustered data. So some of these things that we work with in statistics actually are quite good in prediction as well. And we have a lot of overlap between machine learning models and more classical models in statistics that are used for inference. For example, GAMS would be a good example where we have basis functions. We allow we can use it for inference, but it's also quite good for prediction because the slopes aren't perfectly linear. They're allowed to curve when we apply penalized splines. So often classical statistical tools are used in a prediction framework as well, and often quite good. Okay, but sometimes our goal is more prediction. So for example, we might want to have a simple decision-making heuristic in a hospital or for a diagnosis or something like that. And so a decision tree might be good for something like this. Sometimes the goal is to predict weights for inverse probability weighting or something like that. You can use machine learning for this or getting propensity scores. So it can be quite handy in the field of statistics as well. Okay, so probably 95% of the time in my consultations, it's more classical statistics or higher. But occasionally we do have people who want to do these predictions. So we had somebody I was working with used XGBoost to predict who had pulmonary hypertension just from MRI images and got 100% accuracy in the test set. So it is quite powerful, and it can do quite impressive things. Okay. So I guess one of the main things I wanted to talk about today was this bias variance trade-off, as it's called in machine learning language. So there's this classic image. Normally we want a good fit here, right? We do this one on the far left. This image on the far left is sort of underfitted. We're just putting a linear slope through something. It's clearly not a linear relationship. We might have a better fit in the middle, and on the far right, we've got something which is overfitted, right? So clearly the one on the far right, we're overfitting the the data that the model's trained on, right? It's pretty much picking up every single point. So this one on the far right probably isn't going to generalize well to unseen data. Okay. Right. So we don't want to do this on the far right. We want to get a good fit, which is an optimal trade-off between bias and variance, overfitting and underfitting. So I'll talk a bit about lasso and ridge regression first, because this sort of comes up later on for XGBoost. So I thought I'd start here. We've done quite a few seminars on lasso and ridge regression, but just a bit of a reminder. So these are typically quite good for high dimensional data, or where you have a lot of predictor variables and you might be agnostic about what the final model might look like. And maybe some of these predictor variables aren't very important. We don't know, right? So it can be quite good for this sorts of data sets. And so if you had imagined some relationship between a response variable and a predictor variable, you might do a linear regression and you find this relationship. So the beta is 3 or whatever it is. What lasso and ridge regression do is actually introduce a bias. So this original beta coefficient is shrunk down towards 0. So if you like, it's kind of adopting a skeptical view of that coefficient. It works by penalizing the sum. So for lasso, firstly, penalizes the sum of the slopes, the absolute values of the slopes, the beta coefficients, by a penalty lambda. And we can find out what lambda is through cross-validation, the optimal lambda predict. So when I first learned about this many years ago, I was kind of shocked. Like, why would you want to introduce bias into your model, right? The idea is that by doing that, we reduce variance, and sometimes that trade-off is going to give you better predictions. So yeah, you introduce this small bias. With lasso regression, you can actually get this coefficient to be all the way down to 0. So, and Nixon talked about this in one of his talks. It can be used, lasso can be used as a way of L0, I guess, regularization as well, where you completely penalize a model, a coefficient. So you basically can use it as covariate selection or feature selection or screening. So we only include in the next stage of our modeling variables which are reasonably important. Okay, ridge regression. I'll talk about that in a second. Oh, right. So the penalty is applied unevenly. So because this penalizes the sum of the slopes, predictors which are found to be important in predicting the response variable, those coefficients aren't penalized as heavily as coefficients which are not as predictive. Okay. All right. So ridge regression is similar to lasso, except it's penalizes the sum of the slopes squared, which means that the predictors will never actually get to 0, although they might be shrunk by a lot. So it'll include all your predictive variables, but they might have a really, really small coefficient. And then elastic net is a combination of L1 and L2 regularization, like penalties. So it's going to, it can also shrink it to 0, but it might not as well. Basically, elastic net is really just a combination of lasso and ridge regression. It has 2 hyperparameters. One is the lasso, the penalty, and one is alpha, which is like a toggle between 0 and 1 between lasso and ridge regression. And we can find what the optimal value of each is through like a grid search, for example. So I use this Boston housing data example. In this one, interestingly, turned out that the red is lasso. One on the far left, the gray column, is just regular linear regression. And blue is ridge. I think sorry, yeah, blue is ridge, green is elastic net. And then dark green is elastic net with extra penalties, so a bigger lambda. And you can see that the lasso, actually, there wasn't that much of a penalty on most of the covariates. The lambda was really small. So kind of suggests that all of these variables are kind of important in predicting house values. So this data set is a bunch of predictors for house prices. Okay, blue, we can see in this particular example, some ridge regression is penalized some covariates more than others, and elastic net has as well. Yeah, so if you look here, it's a bit hard to see, but in this table, the rooms, number of rooms, actually in Lasso, that's not penalized at all. Number of low status people, as it's called, that hasn't been shrunk at all in Lasso. A couple of these covariates have. Yeah, so anyway, that's just an example. Okay, so moving on. So in machine learning, often if you see this top part of the image, often your data set will be split into, for example, a training test, a training set and a test set. Sometimes you have 3 partitions, so you could have a training set, a test set, and a validation set, which I quite like as well. But to reduce overfitting, but then it means that you need more data. Right. So if you have a limited amount of data, be careful about doing that. But I think that's a nice approach. Anyway, this is quite a common protocol. So you'll split your data into training and test, and then within the training data, you might want to use k-fold cross validation. So here it's 5 folds, and you use, for example, you might use on the first row here. I don't know why I don't have a mouse, but on the first row, you might fold one in pink. That might be the test set, and the other folds will be used as training. And then you're going to get 5 different out of sample results within your training data. Okay, and then we can tune our hyperparameters. So hyperparameters are like parameters often that are controlling the complexity of the model. Okay, and other things too, but typically they're about the complexity of the model. And so there's a few ways of finding these hyperparameters. One is just to use the defaults, which, if you're just getting started in machine learning, start with the defaults, that's fine. Have a look at how it works, play around with it. Then you can try things like a grid search, which I'll explain more about in a second. Perhaps actually I'll use this plot here. So a grid search, say you've got 2 hyperparameters, the top left image here, sorry. You might have 2 hyperparameters, x1 and x2, and you might try all of these different combinations of hyperparameters and find out which one gives us the best prediction in our validation set, in the cross-validation internal training set. So that's quite good. It can be quite intensive. So if you want to have really, really small, fine-grained changes in each of these parameters, it's going to take longer. So it's like a sort of, a dumb method, so to speak. It can be quite computationally intensive. It's just going to test every combination and find the best performance out of sample. So there's that. One option here with a grid search is to start with quite a coarse grid, and then you can make that grid a bit finer if you want. Another approach is like a random search. So you'll just look at random values and find the best combination. And then there's sort of a bit more modern approach is Bayesian optimization. So this is quite a bit more of an elegant approach. So what will happen in the algorithm is it'll test, in the first stage, it'll test random points. And this is in multivariate space, right? So there might be 7 hyperparameters you can test. You can find a combination of all of those. Obviously, the more dimensions you have, that's going to increase it, the time to search the search space by a power, right? So add enough extra one, you're going to have a much bigger search space. But anyway, so what this will do is in multivariate space is test all the combinations of hyperparameters. Starts with randomly testing in the first spot, and then it uses a Bayesian updating approach where it will create a map of areas which have lower error, for example. So maybe these blue points here, and then it applies a Gaussian kernel in multivariate space. So you can, and so over time, what it'll do is spend more and more time on these local minima, and so it's a way of finding. So it starts off quite broad, and then it starts narrowing down onto areas that have better performance. So it's quite an elegant approach. So it constantly updates itself, and it's a good way to find your hyperparameters. One thing about doing this is the hyperparameters themselves can become overfitted in a sense to your training data, but and so you might see a big difference between your cross-validation performance, which will look really good because the hyperparameter has been tuned on that. And then you might see a bigger drop in your test performance. That's one reason why it can be good to have a train test validate approach. But anyway, this is a good approach. Typically, you're going to get better results in your machine learning when you're using at least a grid search or Bayesian optimization. I find works quite well. It's more efficient instead of testing every single combination. Okay, moving on. So going back to something like a decision tree. This is quite an old machine learning tool. One thing I like about these is that they're sort of intrinsically interpretable. So in this example, you look on the right, we have number of rooms. So, and then you have a split point. So is there less than 6.9 rooms? If yes, then you go down this left side of the decision tree. And then you have another question, how is the percentage of low status people, it's very politically correct, is that over the 15%? And if yes, you go to the left again, and then we have another decision point, is crime greater than 7.5 per 100 or whatever? And then yes, okay, so we have, this is like the lowest SaaS prices over here. So these are in like thousands of dollars, I think. This is back in the 70s, so that's why the numbers are quite low. And yeah, but this is just using the default hyperparameters. We get a pretty simple tree. Most of the covariates in the data, it's like 13 covariates or so. We don't see most of them. We're just looking at status, rooms, crime. Anyway, so one benefit of a simpler tree is if your goal isn't purely prediction, again, sometimes if it's a doctor trying to make a quick decision heuristic, a simpler tree might be better. But for prediction, we should tune our hyperparameters. Or if we're using prediction, these decision trees themselves probably aren't going to be our best bet. But they do offer sometimes a reasonable balance between interpretability and performance. So I've used these with clients before. So in this data set here, we've got on our training set, don't focus too much on the training set, but the R squared was 82%, and mean squared error, which mean squared error 3.9. And then in the test set, our R-squared drops. This is standard. It's usually lower compared to our training, 70%, but we've got a quite interpretable model. Okay, so this isn't really a black box system. Other ML algorithms can be. So here are some of the hyperparameters we have. The main one you want to tune here is complexity parameter. So I went and did that with Bayesian optimization. Oh, I should show you. This is what the predicted values look like. So you can see it's quite, the predicted values on the y-axis, they're quite boxy, right? They're not smooth, right? We've only got, what, 8 different predicted values. So, it's a bit boxy and rough. Maybe we want something smoother than that. So next I used Bayesian optimization to find my hyperparameters. So I found it was much more complex decision tree. Sometimes it's more, sometimes it's less than the defaults. And so, yeah, we have a lot more information here. And we have better test performance. So it's gone up, like R-squared's gone up by 0.7 to 0.8, roughly. So improved. R-squared, while it's quite interpretable, let's keep in mind it's not an absolute measure of error. Mean squared error is, or mean squared error, are measuring absolute error. Okay, and so when we have a more complex tree, we can get a curve which is a bit smoother, right? So we don't get that. It's not as boxy as it was. Still a bit boxy, but not as bad. Yeah. Okay. So these are the hyperparameters it found. Okay. And we noticed that in the cross-validation set, we have performance which is a little bit better than the test set, which is interesting. Could be, who knows, it could be because we've tuned our hyperparameters on these same folds. So it's hard to know, but anyway. Okay. Next would be random forests. So anything else I need to say? No, that's okay. So it's like decision trees, but there's hundreds of decision trees. So over here we had, let's go back here. This is maybe one simple tree. In random forests, we make like hundreds of trees like this, except there's a few differences. Each tree is going to see a different random subset of data, maybe 70% of your training data. And so it's going to make different split points. And then you're going to have hundreds of different predictions. And then you average them over over all of these models. So yeah, each tree gets a random bag of data and models that. And here was my curve over here. It's sort of smoother. In the predictions, we have a lot more predicted values, and we've got a huge increase actually in the test performance, lower error, higher R-squared. So typically we have much better performance than a single decision tree. That's a common result. That's not surprising, and we get a smoother sort of curve. One disadvantage of this is it's not as immediately interpretable. So we can go and look at there's some techniques we can use to look at how to interpret how this black box system is working. Right, so we're trying to get some explainability. So it can look at a few things called like variable importance would be one. If you look at the top right, we can see the number of rooms in the house and the number of low status people. These are the two most important predictors. And this is like it basically tests each predictor and asks if we split on this predictor, do we improve the what's called the purity of the nodes? So do you get better separation of your data by making splits on this variable? That's And we've got there's a lot of different metrics here. A lot of different packages can be used to do this. Another quite common one would be permutation importance. So in permutation importance, you would randomly shuffle, like at one variable at a time, you would randomly shuffle the values in that predictor from other cases. So you would be using real data, but from mixing up your data. And then looking at the decline in accuracy. So if you had a variable which wasn't important, it wouldn't matter if you permutated randomly different possible values, probably get a similar result. If you had a really important predictor and you randomly shuffled the predictor values from other cases, you would see a big drop in accuracy. Okay, so that's another approach. And then there's SHAP analysis as well, which is sort of gold standard as far as I understand these days. So basically, it's trying to understand for every single prediction, it tries to understand how important each individual predictor is. Another thing about random forests, I thought I should mention is, I haven't talked about this too much, but in classical statistics, often the goal is inference. So we're trying to talk about beta coefficients, our slopes, confidence intervals, p-values. P-values can be also, there's a couple of papers on this where they look at variable importance by permutation. And they found that they reported that this is asymptotically normal, this importance metric. And so they thought, okay, we can get a p-value from that. It sounds, I had a look at a couple of papers and it sounds reasonable. But I'm just still a little skeptical of that because the algorithms they are using, I think they're using the training data. And these are quite complex models, so it could potentially be overfitting. So I'm a little skeptical of that, but there is it is a thing which you can look into. You can potentially manually use the test set and extract p-values if you wanted to do that. So yeah, you may want to know how does the number of rooms affect the price. So you can still print out like a partial dependence plot on the bottom right. You can get the SHAP values. Those SHAP values is like telling us how important each variable is. Sorry, as you change a variable, how does that change? How does that change your response variable? How important is it? Okay, so here's 0, close to the bottom. Most values are around 0 or just below on the left, but when you get the 7 rooms or more, this variable now becomes quite important in predicting the price. That's one way of thinking about it. And then on the top left, this is just the regular scatter plot from the raw data. Okay. Yeah. Okay, so the next one is XGBoost. So this is this performs really, really well. I've had a lot of experience in playing around with machine learning models. And very frequently I find this performs really, really well. Often wins competitions on Kaggle and where people are given new data and they try and make predictions on the test set. So it's a little bit different to random forest. So in random forest, it works in parallel. Every tree sees different data, but it doesn't know about the existence of any other tree. In XGBoost, it works sequentially. And so each tree is generated based on the prediction errors or the residuals of the previous tree, at least in regression. It's done by the gradient divided by the second derivative, which in regression is just the prediction error. But I should mention just a quick aside, all of these models, so trees, random forest, XGBoost, these are also excellent at classification, which might be binary logistic classification, or you might have 4 or 5 potential outcomes. These work really well in that as well. Okay. Anyway, so what happens is there's a gradient descent. So there's this loss function which it tries to minimize, and it does that by using the first prediction. The first tree might actually just be the mean, or it might be a simple decision tree. and then you look at those predictions, and then those prediction errors are then fed forward into the next round. So the next tree that's made, all it actually sees are prediction errors. It doesn't see your Y values, it sees the gradients. So each observation has a gradient, which is just 2 times the prediction error, in regression at least. And it tries to model those prediction errors. So just for example, I'll try to explain this. Here might be some curve, your first tree, for example, might give you something like this, and here are your residuals. The next tree's goal is to reduce these prediction errors. And it does it by the gradient divided by the second derivative. But we don't want to just simply reduce these prediction errors down to 0, because if we did that, we would have this problem that we talked about earlier, where we have like overfitted data, right? We don't want those we don't want to get a tree that predicts those residuals so perfectly that, you know, it's overfitted. So it includes a sort of a dampener. So it uses L1 and L2 regularization, so lasso ridge penalties on what's called the leaf weights, which I'll explain, and also some other complexity parameters like gamma. Okay, so what I think is quite interesting about this is that it after each iteration, it gives more and more attention to cases which are hard to classify, or cases where the predictions are quite off. And so and it's going to pay twice as much attention to like prediction error of, you know, so if there's a prediction error in case 1 of 1 and a prediction error of 2 in another one, it's going to pay 4 times more attention to this prediction error of 2 versus 1, based on the gradient. So yeah, so anyway, it does that, and this is sort of actually observed in psychology as well. So animals really will pay more attention to things that are surprising or unusual or different to what they expect, right? And then we update. That's how we learn. In fact, the biggest stimulus for learning, it's found in mammals. One of the biggest ones is just prediction error, right? So that makes us learn more. Okay, so yeah, so I think I've kind of explained that here already. So yeah, we don't want to overfit this reduction in the prediction error. You could say that it's sort of working independent processes, so it's trying to reduce prediction error, but it's trying to control the variance associated with that. So it prevents overfitting with like quite a lot of penalty terms. And if you don't need to worry about this formula, but it's there if you want to have a look at it later. So basically, this objective function includes on the right-hand side of that is the penalty terms, the regularization term. So that's got gamma in it, and that's down here. Gamma times the number of leaves in a tree, plus you have lambda, and we have alpha. And so L1 and L2 regularization on these leaf weights. We can try and explain this a bit more in the next slide. So, for example, these blue dots might be if it's regression, they might be your prediction errors, residuals. And so what it tries to do is group different prediction errors together and then split on some feature or some variable to group those together so that we get a big gain. We have one split on feature X here, 3.5 and another 5.5. And so then we get these leaf weights, and these weights are in terms of units of the prediction error of your response variable, right? Thousands of dollars or whatever. Okay. So yeah, it tries to group. Again, it's a bit different. It's not looking at, it's not really, so to speak, seeing your Y, your response variable. It's seeing prediction errors, and it's trying to find features or split points which can group like things that are like high prediction error, negative prediction error, whatever. It's going to group those together by these leaf weights. So these leaf weights down here are now going to be penalized by L1, L2 regularization. So basically, some of them might not exist because they might, the lasso penalty might take them down to 0. So they might, that's going to make the tree less complicated. And then we also have this gamma penalty. So a split point has got to have achieved some minimum amount of gain in the difference in prediction error. And if we set gamma to a higher value, it's going to have a higher penalty. And so what ends up happening is these XGBoost trees are actually really simple. They're actually really shallow trees typically. But then there's many of them, and they're focused increasingly on harder to classify cases. Interestingly, the performance in the test set here, this is just one example, was actually slightly lower than the random forest, ballpark similar, but yeah, slightly lower. But that's typically I would find XGBoost would I'd normally find it predicts better out of sample, but you know, with the Bayesian optimization, random forest can do quite well too. So not too surprising, I guess. But yeah, this is an excellent, I would highly recommend if you're looking at doing machine learning, either classification or regression. This is a great algorithm to use. Okay. What else? Okay, so a bit more information. You can look at this a bit later, but yeah, as you can see, there's quite a few hyperparameters. We can choose some of these values. We can increase our gamma. So you know, it's so aggressive in trying to reduce bias, trying to fit the data, that you might want to sort of increase your gamma a little bit, or have push up these penalties. Obviously, you can play around with it, obviously, or you know, just while you're getting to understand how the model works, and then go and potentially do some hyperparameter tuning. Yeah, but anyway, moving on. Yeah. Yeah, so tuning the hyperparameters can take longer, right? Because you've got more of them. Next, I thought I'd talk about superlearner. So this is all of these. You can see all these packages here. Oh, that's nice. So okay, it's about 10 years old now, superlearner. So some of these models are a little bit dated. The default GAM model isn't as good as the MGCV package in GAMs, but anyway, it's okay because you can create your own custom machine learning models. So you can use any model, really, and then just get superlearner to use it. So what it does is that it tests a bunch of different models, and first of all, let's focus on the top right. Sorry about that. On the top right slide, this is internal training, and so these are the risk. I think this is sort of mean squared error. Yeah, mean squared error on the top right, and then to the right of that is the coefficient. So this is what basically superlearner is going to find out how well each model performed, and then given the possible, I just used a subsample of some of these possible algorithms. But so what it'll do is look at how well each model works in the cross-validation step, and then it assigns a weight to that based on its performance. So we can see here that so Ranger, that's a type of random forest. The first one I had was the coefficient. That's the weight. So that was weighted down to 0. So it didn't perform that well. The next was an XGBoost. That was had quite low mean squared error, 9.6, and it's weighted at 64%. Right. Then the decision tree by itself, quite high mean squared error, 0. I just use the defaults in these just for, but you can absolutely tune these hyperparameters within Superlearner, or again, make your own models first. What else? Then there's lasso in there, or GLNet, so L1 or L2. That doesn't fit into it. Interestingly, the lasso and ridge regression didn't improve over linear regression in this data set. Interaction model, where we allow interactions between variables, performed okay. It had 13 mean squared error, and it was weighted at 30%. And then, okay, the GAM, this particular GAM didn't do that well. I played around with it a bit, adding my own GAM in there, which did a lot better. But anyway. So, and then we can see out of sample. So this bottom right is a performance out of sample. And interestingly, the best was this random forest, which was actually not even included by Superlearner. Next was the other random forest, performed quite well. So these are quite low errors. Superlearner is the ensemble. So the ensemble of which was 3 of these: XGBoost, random forest, and step interaction. That performed the 3rd best. And then next was XGBoost. However, it's still what I could have done if I was just looking at this cross-validation thing. I would just go, oh, XGBoost did the best. It's easily had the lowest cross-validation error. So why don't I just use that? But then if I did that, I would have got a worse performance, which is, I would have got 3.5 versus 3.3 in terms of mean squared error, right? So by weighting these other possibly good algorithms together, we can improve the prediction of what, right? So just random differences in our test set, there's a lot of reasons we can see these differences. Could be overfitting, hard to know. But I recommend using this package. If I was doing a big machine learning project, if I was doing it, I would probably get a bunch of algorithms I know are good, tune those hyperparameters, then bring them into Superlearner. Probably not using the defaults, but and then just plugging that in, and works pretty well. So moving on, just winding up really, just recommendations. Try to tune your hyperparameters. They can, I guess, become a little overfit to your training sample, but still, on average, is a good idea to do. Have a look at the Carrot package, for example. It has a good, if you're using R, there's a lot in Python as well. Carrot has a lot of machine learning examples and a lot of new algorithms come through all the time. And the third point, I would say, don't use your test set to train your model. I see people doing this where they're using their test set to go, oh, actually, maybe I'll just go and change my hyperparameters again. It's like, no, don't do that. don't use your test set to train the model. Again, if you want to, maybe if you find yourself doing that sort of thing, perhaps partition your data into training, test, validate, and just only use your validation step just for measuring out of sample performance. Okay. I also made a glossary of terms here for machine learning, which you can look at. Yeah, but that's it. Any questions?